This is the Friday, August 28th lecture for Math 1175, Section 4. In Section 7.5 of the textbook, we'll take a look at the strategy for integration. In the textbook, Section 7.5, the problems assigned for practice are these 10 problems. On page 503 of the textbook is a table of basic integration formulas that you should be familiar with or know how to derive. As you have seen and have probably experienced for yourselves, different integration strategies sometimes work when evaluating a particular integral. Here's a brief listing of the integration strategy given in the textbook in section 7.5. The first one, simplify the integrand if possible. Number two, look for an obvious substitution to apply the substitution rule or a trigonometric substitution. Step three, classify the integrand according to its form. And if you're still unsure about how to proceed, just try again with a different approach. So far this semester, we have seen the following. The substitution rule from Chapter 5, Section 5. Integration by parts, Chapter 7, Section 1. Trigonometric integrals, Chapter 7, Section 2. Trigonometric substitution, Chapter 7, Section 3, and then the partial fractions method for rational functions, Chapter 7, Section 4. On the following pages are integrals to integrate by whatever means we like. Okay, so here is our first example. The indefinite integral of dx over x plus x times the square root of x. Since we have a square root of x in the denominator, I'm going to assign u to be the square root of x. And du is 1 over 2 times the square root of x dx. We want to know what dx is, so if we multiply both sides by 2 times the square root of x, we get 2 times the square root of x times du equals dx. But the square root of x is what u is, so this just becomes 2u times du for dx. Okay, now we can do the other substitutions. If u is equal to the square root of x, then u to the second equals x. So in the numerator, replace dx with 2u du. Replace x with u squared. And then plus, well, in the original denominator, we have a plus x times the square root of x. So this is u to the second times u, or u to the third. And notice that in the integrand, the numerator and denominator have a factor of u in common. So u divided by u cancels, and we can simplify the integrand and write it as the indefinite integral of 2 divided by u times one plus u squared. Sorry, 1 plus u. I should have put another step in showing the cancellation. Yeah, but this is right, and this is a rational function. The integrand is a rational function. So we're going to rewrite it as an integral of a over u plus b over 1 plus u, or u plus 1 du. And then once we know what the values of a and b are, then we'll be able to find the indefinite integral. So we'll do that work separately here. So we have 2 over u times u plus 1 equals a over u plus b over u plus 1. We multiply every term on both sides by u times u plus 1, and we get this equation. 2 equals a times u plus 1 plus b times u. So first, let's assign u to be 0. Replace every u with 0, and we get the equation 2 equals a times 0 plus 1, or 2 equals a times 1, or a, and b times 0 is 0, so we find that the value of a is 2. Okay, the other factor, u plus 1, if we let u be equal to -1 and replace u with -1, we get 2 equals a times 0, because -1 plus 1 is 0, equals b times -1. And then we solve this for b, and we find that b is equal to -2. Okay, so now we can proceed to evaluate the integral. So since a is 2, we have the indefinite integral of 2 over u. B is -2, so I'm going to write this as minus 2 over u plus 1 du. Then the indefinite integral of 2 over u with respect to u is 2 times the natural log of u. And then from that, we subtract the antiderivative of 2 over u plus 1, which is minus 2 times the natural log of u plus 1, and then plus a constant. And then remember that u is the square root of x. That was our original substitution. So our final result is 2 times the natural log of the square root of x minus 2 times the natural log of the square root of x plus 1, and then plus a constant. Okay, in the next example, we have the indefinite integral of sine of t to the 5th times cosine of t to the 4th dt. Since we have an odd power of sine, we're going to use one of the sine of t's. So sine of t to the 5th is sine of t to the 4th times sine of t. So I'm going to rewrite the integrand as the sine of t to the 4th times cosine of t to the 4th times sine of t dt. And now I'm going to replace sine of t to the 4th with an expression in terms of cosine. So sine of t to the 4th is just sine of t to the 2nd squared. So I'll write that sine of t to the 2nd squared. And then we multiply that by everything else, cosine of t to the 4th times sine of t dt. And sine of t to the 2nd is 1 minus cosine of t to the 2nd. So we'll replace sine of t to the 2nd with 1 minus cosine of t to the 2nd. quantity squared times cosine of t to the fourth times sine of t dt. Then we'll square this quantity, 1 minus cosine of t squared. When we square that, we'll get 1 minus 2 times cosine of t squared plus cosine of t to the fourth. This is multiplied by cosine of t to the fourth times sine of t dt. Then we distribute multiplication by cosine of t to the fourth through this quantity. So we get the indefinite integral of cosine of t to the fourth minus 2 times cosine of t to the sixth plus cosine of t to the eighth multiplied by sine of t dt. Now we'll use the substitution rule. We will assign u to be cosine of t, and du then is negative sine of t dt, and then negative du is sine of t dt. And you can see that we have a sine of t dt in that integrand above. So we make substitutions, and we transform this integral. Cosine of t to the fourth becomes u to the fourth, and then minus 2u to the sixth plus u to the eighth, and then replace sine of t dt with negative du. So this is like negative 1 times du. So we'll bring the negative factor out front. We'll apply that last. And then we'll just find antiderivatives of these three terms in u. So the antiderivative of u to the fourth with respect to u is u to the fifth over 5. And then we have minus 2/7 u to the seventh, and then plus 1/9 u to the ninth plus a constant. And then in the last step, we'll replace u with cosine of t and also distribute multiplication by negative 1. So our final result is negative cosine of t to the fifth over 5. And then we're subtracting a negative, so that's plus 2/7 times cosine of t to the seventh. And then we're subtracting 1/9 times cosine of t to the ninth plus a constant. Hey, this is the final result of that indefinite integral that we started with. In the next example, the indefinite integral of x times e to the negative 2x dx. So on this one, we'll use integration by parts because the integrand is a product of a polynomial and an exponential function. So if I pick u to be x and pick dv to be e to the negative 2x, then if u is x, du is dx. And v is negative 1/2 times e to the negative 2x. For the dv part, it should also have the dx attached. dv is e to the negative 2x dx. Okay, so if we apply the integration by parts formula, u times v, so x times negative 1/2 e to the negative 2x. This will be negative 1/2 x times e to the negative 2x. And then we're subtracting the indefinite integral of v du. So we're subtracting the indefinite integral of negative 1/2 e to the negative 2x dx. Okay, we'll simplify this a little more. Let's write it as negative 1/2 x times e to the negative 2x. And we're subtracting negative 1/2, so we can write plus 1/2 times the indefinite integral of e to the negative 2x dx. And now we're just a step or two away from the final result. Negative 1/2 x e to the negative 2x plus 1/2 times the antiderivative of e to the negative 2x, which is negative 1/2 e to the negative 2x, plus a constant. And then the last step, negative 1/2 times x times e to the negative 2x. And here we're adding a negative, so plus 1/2 times negative 1/2. So we write this as minus 1/4 times e to the negative 2x plus a constant. Okay, so that's the result of the integration by parts example. In the next example, we have the indefinite integral of the square root of 1 plus x over 1 minus x. Okay, on this one, let's multiply the integrand by 1 in the form square root of 1 plus x over 1 plus x dx. So for values of x that are not equal to negative 1, the square root of 1 plus x over 1 plus x is equal to 1. So we're just multiplying by 1, which doesn't change the value. Okay, so the square root of 1 plus x over 1 minus x times the square root of 1 plus x over 1 plus x, this can be written as a single square root. So we multiply the two numerators, 1 plus x times 1 plus x, so we get 1 plus x squared in the numerator. And then in the denominator of the square root, 1 minus x times 1 plus x, that works out to be 1 minus x squared, and then dx. Okay, in the numerator, the square root of 1 plus x quantity squared is just 1 plus x. So we just write 1 plus x in the numerator. And in the denominator, we have the square root of 1 minus x squared, and then times dx. Okay, in the denominator, inside the square root, we have 1 minus x squared. So that suggests perhaps the trig substitution, x equals sine of theta. And so dx will be cosine of theta d theta. We can do a little bit of work that's going to go into this denominator. Let's just look at the square root of 1 minus x squared with x replaced with sine of theta. So this this denominator will become the square root of 1 minus sine of theta squared. But 1 minus sine of theta squared is cosine of theta squared, so we get the square root of cosine of theta squared, but the square root of cosine of theta squared is cosine of theta. Okay, so we make all these substitutions. In the numerator, we replace 1 plus x with 1 plus sine of theta. In the denominator, replace the square root of 1 minus x squared with cosine theta. And then dx is cosine of theta d theta. We can simplify the integrand. That's one of the steps in the strategy for integrating. Simplify the integrand. Cosine divided by cosine is 1. So we get the indefinite integral of 1 plus sine of theta d theta. So we can easily find the antiderivatives. So the antiderivative of 1 with respect to theta is theta. The antiderivative of sine of theta with respect to theta is negative cosine theta. And then plus a constant. Okay, but we remember our original substitution. X equals sine of theta. So if x is sine of theta, that means the inverse sine of x is theta. So this is going to go here. And we also need to determine what cosine of theta is based upon the fact that x equals sine of theta. So we can use right triangle trigonometry to help us. So if this is our angle theta, and if the sine of theta is x, then the length of the opposite side to theta is x, the hypotenuse is 1. And then if we use the Pythagorean theorem, the adjacent side to theta is the square root of 1 minus x squared. And the cosine of theta, which is what we want, cosine of theta adjacent over hypotenuse, which will just be the square root of 1 minus x squared. Okay, so now we can write the result of the original indefinite integral in terms of x. So theta is the inverse sine of x, the angle whose sine is x. And then we're subtracting cosine of theta, which is minus the square root of 1 minus x squared, and then plus a constant. Okay, the next page. And this one, we have a definite integral of e to the arctangent of y over 1 plus y squared dy, as y ranges from -1 to 1. Since the integrand is a function of y, the limits of integration are y values. So we see e to the arctangent of y. So if we assign u to be the arctangent of y, if you prefer, you can use, instead of arctangent of y, just use inverse tangent of y. Okay, so we need to find du. So one way to do it is take the tangent of both sides. So we get tangent of u equals y. And since u is a function of y, we're going to find du by using the chain rule. So on the left-hand side, we take the derivative of tangent of u, which is secant of u squared, and then the differential du. And then on the right-hand side, the derivative of y with respect to y is, well, here we just write the differential dy. The derivative of y with respect to y is 1, but then when we multiply it by the differential dy, we get dy. Okay, so we solve for du, divide both sides by secant of u squared, so we get du equals dy over secant of u squared. Secant of u squared is the reciprocal of cosine of u squared, so we can rewrite this as cosine of u squared dy. So we want to replace cosine of u squared with an expression in terms of y. Okay, that's what we use our substitution to do. Our substitution is u is equal to the inverse tangent of y. So we can use right triangle trigonometry again. So u is the angle whose tangent is y. That's what this says. Tangent of u equals y. So if u is the angle and the tangent of u is equal to y, then the opposite side of u is y, and the adjacent side is 1. And then the hypotenuse is the square root of 1 plus y squared. And so cosine of u is 1 over the square root of 1 plus y squared. And we want to know what cosine of u squared is, so just square both sides. Cosine of u squared is 1 over 1 plus y squared. Okay, so du then. That's what we want. Du is 1 over 1 plus y squared dy. I'll just write it as dy over 1 plus y squared. Okay, now we can make substitutions into the definite integral. For now, I'll just leave the limits until a little bit later. But we have e to the u, because u is inverse tangent of y. And we see that we have dy over 1 plus y squared, and that's exactly what du is. So we get the integrand is just e to the u du. And the limits of this integral have to be u values. Okay, so we use this assignment or substitution. When y is equal to -1, when y is equal to the lower limit, -1, the u value is the arctangent of -1, or the inverse tangent of -1. So this is like asking, what angle between negative pi over 2 and pi over 2 is the tangent equal to negative 1? And the answer is negative pi over 4. The tangent of negative pi over 4 is negative 1. So the lower limit of this definite integral in the variable u is negative pi over 4. And then the same reasoning when the y value is the upper limit 1, when y equals 1, the u value is the inverse tangent of 1. The angle whose tangent is 1 is pi over 4. Remember, the range of the inverse tangent function is between negative pi over 2 and pi over 2. So in that interval, tangent of pi over 4 equals 1. So the upper limit is pi over 4. Okay, so down here in this space, the indefinite integral of e to the u du is just e to the u. And we're evaluating it on the interval from u equals negative pi over 4 to u equals pi over 4. So here's the final answer. E to the pi over 4 minus e to the negative pi over 4. This is the answer to our definite integral. Okay, the next example, the indefinite integral of x to the third divided by the cubed root of x squared plus 1 dx. Inside the cubed root, we see x squared plus 1. So that suggests, the x squared plus 1 suggests that we pick x to be tangent of theta. And so dx will be secant of theta squared d theta. Inside the cubed root, when we replace x with tangent of theta, inside we'll have tangent of theta squared plus 1, which will become secant of theta squared. So we can make all of our substitutions. In the numerator, x to the third, this is tangent of theta to the third. And then we have the cubed root of secant of theta squared. And then we multiply by dx, which is secant of theta squared d theta. Okay, the cubed root of secant of theta squared, that's equivalent to secant of theta to the 2/3 power. And this secant of theta squared, that's equivalent to secant of theta to the 6/3 power. So when we simplify secant of theta to the 6/3 divided by secant of theta to the 2/3, we're just going to get secant of theta to the 4/3 power. Just using properties of exponents. Okay, so the next step, we have a tangent of theta to the third, so I'm going to borrow a tangent of theta from that, leaving tangent of theta to the second behind. And from secant of theta to the 4/3, I'm going to borrow secant of theta, leaving secant of theta to the 1/3 behind. So with that in mind, let's write down what we have. We have tangent of theta squared times secant of theta to the 1/3, or the cubed root of secant of theta, and then multiplied by secant of theta tangent of theta d theta. Okay, the motivation for that maneuver is secant of theta tangent of theta is the derivative of secant of theta. And we can replace tangent of theta squared with secant of theta squared minus 1. So that will be the next step. Replace tangent of theta squared with secant of theta squared minus 1, which we multiply by secant of theta to the 1/3 times secant of theta tangent of theta d theta. Let's distribute multiplication by secant of theta to the 1/3. So this is going to become the indefinite integral of secant of theta to the 7/3, because secant of theta squared is the same as secant of theta to the 6/3. So when we multiply that by secant of theta to the 1/3, we get secant of theta to the 7/3, and then minus secant of theta to the 1/3 times 1, and then multiplied by secant of theta tangent of theta d theta. Well, if you've done this a few times, you don't really need to do the substitution rule, or you don't have to go through all of the steps, but we'll do that anyway. Let's assign u to be secant of theta. And so du is secant of theta tangent of theta d theta. So we see that in the integrand we have du, and the other terms are going to be expressed in terms of u. So our integral then becomes u to the 7/3 minus u to the 1/3 du. So this is a simple indefinite integral to evaluate. So we add 1 to 7/3 and divide by the same number, so we're going to get 3/10 u to the 10/3. And then for the antiderivative of u to the 1/3, we're going to get minus 3/4 times u to the 4/3, and then plus a constant. Okay. Well, our original integral is in terms of x. And we've made two different substitutions. So we can first determine what u is in terms of theta, and then we can determine what theta is in terms of x. So u is just secant of theta. So if we can determine what secant of theta is in terms of x, then we'll essentially be done. Okay, so let's use the right triangle trigonometry and the assignment x equals tangent of theta. So x equals tangent of theta. So if theta is the angle and the tangent is x, we get x over 1. And then the hypotenuse is the square root of x squared plus 1. And secant of theta That's the reciprocal of cosine. So this is just the square root of x squared plus 1 over 1, or the square root of x squared plus 1. And since u is secant of theta, we can just replace u with the square root of x squared plus 1. Okay, so I'm going to think of the square root of x squared plus 1 as the quantity x squared plus 1 to the 1/2. Okay, so we'll make our substitutions. We get 3/10, and then I'm replacing u with x squared plus 1 to the 1/2. And then that is raised to the 10/3 power. And then the next term, minus 3/4 times the quantity x squared plus 1 to the 1/2 raised to the 4/3 power. And then just one more step ought to do it, using properties of exponents. So we get 3/10 times the quantity x squared plus 1. And then we multiply the exponents. 10/3 times 1/2 is 5/3. And then we have minus 3/4 times the quantity x squared plus 1. And here we multiply the exponents, 4/3 times 1/2 to get 2/3, and then plus a constant. Okay, so this is our final result of that indefinite integral. Okay, the next page. So here we're starting out with the indefinite integral of an improper rational function. The degree of the numerator is bigger than the degree of the denominator. So the first thing to do is divide the numerator by the denominator using long division. 2x squared plus 9x plus 4 divided into the numerator, 4x to the third plus 18x squared plus 9x plus 11. So 2x squared goes into 4x to the third 2x times, and then 2x times the divisor, we get 4x to the third plus 18x to the second plus 8x. And then when we subtract, we get 0 plus 0 and then plus x. And so our remainder is x plus 11. So the indefinite integral becomes the indefinite integral of the quotient 2x plus the remainder x plus 11 divided by 2x squared plus 9x plus 4. But note that 2x squared plus 9x plus 4 is nicely factored to 2x plus 1 times x plus 4, and then dx. Okay, so part of the remaining task is to evaluate the integral of this proper rational function. We know what the antiderivative of 2x is. That's just x squared. So let's focus on the second part of that, the indefinite integral of x plus 11 over 2x plus 1 times x plus 4. And we could use partial fractions to do it. Okay, so this is going to involve, since the factors in the denominator are linear, it's going to be the indefinite integral of some number a over 2x plus 1 plus b over x plus 4. And once we know what a and b are, we'll be able to evaluate the integral. Okay, so if we think of x plus 11 over 2x plus 1 times x plus 4 equals a over 2x plus 1 plus b over x plus 4, and then multiply all parts by the denominator 2x plus 1 times x plus 4, we will get the equation x plus 11 equals a times x plus 4 plus b times 2x plus 1. Okay, so one thing we can do to find a and b, since this factor x plus 4 is 0 when x is negative 4, let's first assign x to be negative 4, then replace every x with negative 4. So on the left-hand side, negative 4 plus 11 is 7. This factor is 0. A times 0 is 0. So we get b times the quantity 2 times negative 4 plus 1, or negative 8 plus 1 is negative 7. And then divide both sides by negative 7. We see that b is equal to negative 1. B is equal to negative 1. Okay, the other factor, 2x plus 1, that's 0 when x is negative 1/2. We can replace every x with negative 1/2. So negative 1/2 plus 11, that's 21/2. And then that's equal to a times negative 1/2 plus 4 is 7/2. And this factor is 0 when x is negative 1/2. And so if you multiply both sides by 2/7, we find that a is equal to 3. Okay, so our original integral then, if I write it, including the 2x, we have the indefinite integral of 2x plus 3 over 2x plus 1, because a is 3. Since b is negative 1, we'll write this as minus 1 over x plus 4 dx. And now we can compute the indefinite integral. The antiderivative of 2x is x squared. So on this one, think of 3 over 2x plus 1 as 3/2 times 2 over 2x plus 1. So this will become plus 3/2 times the natural log of 2x plus 1. And then minus the antiderivative of 1 over x plus 4 is just minus the natural log of the absolute value of x plus 4 plus a constant. Okay, the last one, the last problem. Use x equals a times the hyperbolic sine of t to show that the indefinite integral of dx over the square root of x squared plus a squared is equal to the natural log of x plus the square root of x squared plus a squared plus a constant. Okay, so if x is a times the hyperbolic sine of t, then dx is a times the hyperbolic cosine of t, dt. Okay, and it turns out that when you replace x squared with a times hyperbolic sine of t, so let's just look at that in isolation, x squared plus a squared, replace x with a times hyperbolic sine of t, we get a squared times hyperbolic sine of t squared, and then plus a squared. Factor the a squared out, and we get a squared times the hyperbolic sine of t squared plus 1. And the hyperbolic sine of t squared plus 1 is just hyperbolic cosine of t squared. So this becomes a squared times hyperbolic cosine of t squared. Okay, and that's inside the square root. So let's use all our substitutions. So dx is, in the numerator, is a times hyperbolic cosine of t dt. And in the denominator, we have the square root of, I'll go ahead and write it, the square root of a squared times hyperbolic cosine of t squared. So in the numerator, a times hyperbolic cosine of t dt. In the denominator, the square root of a squared times hyperbolic cosine of t squared is a times hyperbolic cosine of t. So a divided by a is 1, hyperbolic cosine of t divided by hyperbolic cosine of t is 1, so we just get dt. And the indefinite integral of dt is t plus a constant. Okay, so now what? We want to know what this is in terms of x. Well, that's where our substitution comes into play. X is equal to a times hyperbolic sine of t. So we're just going to use that fact and solve for t. Okay, but we need a little bit more information. So first I'll write x equals a times hyperbolic sine of t. And this is a times what hyperbolic sine of t is. So hyperbolic sine of t turns out to be e to the x, whoops, sorry, not x, e to the t, because it's hyperbolic sine of t, e to the t minus e to the negative t divided by 2. This is just the definition of hyperbolic sine of t. Okay, so now we're going to solve this equation for t. On the right-hand side, we have a over 2. So let's multiply both sides by the reciprocal of a over 2. That is, multiply both sides by 2 over a. So we get 2 over a x equals e to the t minus e to the negative t. Okay, now let's, well, what should we do first? Let's set one side equal to 0. So I'm going to subtract 2 over ax from both sides. So we get 0 equals e to the t minus 2 over ax minus e to the negative t. Okay, now I'm going to multiply both sides by e to the t. So I'll abbreviate that a little bit, but what I mean by this is multiply every term on both sides of the equation by e to the t. So the left-hand side, 0 times e to the t is still 0. When I multiply e to the t times e to the t, I can write that as e to the 2t. And then the middle term, I multiply that by e to the t, I get minus 2 over ax times e to the t. And then minus e to the negative t times e to the t is e to the 0, but e to the 0 is 1. Okay, this equation is called quadratic in form. Equations that are quadratic in form have some variable part squared. Like this one, we have e to the t squared, and then the middle term involves the part that was squared in the first, like e to the t, and then it's followed by a constant. So this is quadratic in form. We know how to solve every quadratic equation. We can always use the quadratic formula. So if you have an equation that's quadratic in form, we can solve it. So we can even, you could use a substitution if it helps. It's not really necessary. But think of the coefficient of the squared term as 1, because that's what it is. So a is 1. B is negative 2 over ax, because that's the coefficient of the e to the t term. And the constant is negative 1. So a is 1, b is negative 2 over ax, c is negative 1. And the variable part that we're solving for is e to the t. So e to the t is equal to the negative of b. So the negative of negative 2 over ax plus and minus the square root of b squared. So we're going to square negative 2 over ax. And then we're going to subtract 4 times 1 times negative 1. And then we're going to divide it all by 2 times 1. Remember that e to the t is always greater than 0. For any real number t, e to the t is always positive. So if you look closely at what we have over here, we can ignore the solution that we get by subtracting, because the expression that we're subtracting is bigger than the expression that we're subtracting from, which would make the e to the t value negative, which is impossible. So we're going to ignore the minus solution and focus on the plus. Okay, so just a little bit more arithmetic and algebra. The negative of negative 2 over ax is 2 over ax, and then plus. So inside the square root, I'm going to have to pull out another piece of paper, I think. So we're squaring negative 2 over ax, so that's going to be 4x squared over a squared. And then minus negative 4, which is plus 4. And then this is all divided by 2. Yeah, I think I can write a little bit more here. So inside the square root, we can write, instead of plus 4, I can write that as plus 4a squared over a squared. So I get 2 over ax plus I'll go ahead and write it all. The square root of 4x squared plus 4a squared over a squared, all divided by 2. And I'll bring in some more paper. Okay, so we get e to the t equals 2 over ax plus, so in the denominator of the square root, I have a perfect square a squared. And in the numerator, I have a perfect square factor 4. So I'm going to rewrite this square root as the square root of 4 times the square root of the quantity x squared plus a squared. And then the square root of a squared in the denominator is a, and we're dividing this all by 2. So we're getting there. So we have 2 over ax plus 2 times the square root of x squared plus a squared over a. Since I'm dividing by 2, if I divide by 2, that's equivalent to multiplying by 1/2. So I'm just going to multiply all of this by 1/2. And then I'll get e to the t equals x over a. 2 over ax means 2x over a. But when we cancel one factor of 2, we're just going to get x over a. And then 1/2 times this term, the 2's cancel, so I get plus the square root of x squared plus a squared over a. The denominator is common, so I can just write it as x plus the square root of x squared plus a squared all over a. And now we can solve for t. If e to the t is equal to something, then the exponent t is just equal to the natural log of that entire quantity, the natural log of x plus the square root of x squared plus a squared over a. Okay, now what do? Well, we use properties of logarithms. If you have the natural log of a quotient, this is the natural log of the numerator, natural log of x plus the square root of x squared plus a squared minus the natural log of a. But the natural log of a is just a number. It's just a constant. So we can include that with the plus c that we would put with the indefinite integral. Okay, so what we just did, just to remind you, we evaluated the indefinite integral of dx over the square root of x squared plus a squared, and we found that it's equal to the natural log of x plus the square root of x squared plus a squared plus a constant. I'll put c tilde, where this constant c tilde is just negative natural log of a plus the original constant of integration. Okay, so that does it. You got the full treatment if you watch this video. So almost an hour and 5 minutes worth.